What I want to do in this video is explore what's commonly called Pythagoras' identity. And it's often first introduced in pre-calc or calculus in some lower level trigonometry course. And what this essentially does is, in the coordinate plane, it recognizes the intersection of an x horizontal distance and a y vertical distance, and the radius, if you will, of this triangle. That's essentially the slope combined of these two values. And what it does is it equates this in a manner that we could recognize trig functions from this equation. So just like any other right triangle, we could equate these sides by using the Pythagorean theorem. So let's do that right now. We have the square of leg number 1, which in this case will be the horizontal x distance, plus the square of the other leg, which is the vertical y distance, will equal the hypotenuse squared, which in this case we're calling the radius of if you were to theoretically circumscribe a circle around this triangle, and we'll talk about that later once we get into discussions about the unit circle. This would represent the radius of this entire circle. So we have x squared plus y squared equals r squared. You know, that's pretty straightforward. So what we're going to do is this is simply just a matter of simplification. We could divide both sides of this equation by r squared, so let's do that right now. And note that r squared over r squared simplifies down to 1. So now we could use the power rule of algebra 1. We could say that essentially x squared over r squared is simply the quotient x over r raised to the second power. Same thing over here, y squared over r squared rather, simply the same thing as saying y over r all raised to the second power. And again, we just keep this as 1. So what's interesting about this is that now we could sort of apply trigonometry here. If we have some angle theta, which is formed by the intersection of this horizontal y value and the radius that we would theoretically have in a circumscribed, what we're going to later call the unit circle, x over r, well, x is the adjacent side, r is the hypotenuse of this triangular shape over here. So x over r, that's adjacent over hypotenuse. We know from simpler trigonometry and even geometry that adjacent over hypotenuse simplifies down to cosine of this angle theta. And again, there's a square here, so we could write this as cosine squared of theta. Now, y over r. Y, in relation to this angle theta formed over here, that's going to be the opposite side. Y is the opposite side. And r is still going to be the hypotenuse. We know from SOHCAHTOA. So, opposite over hypotenuse, that's going to be equal to sine of this angle theta. And again, we have a square here, so we can apply that. Sine squared of this angle theta. And now we just keep the 1 on the other side. So there we have it. This is perhaps one of Pythagoras' most simple identities. It will prove very useful later on in our further discussions of trigonometry and pre-calculus, but for now, I just want you to recognize how significant this is. We took a simple figure as a right triangle that we made from the intersection of an x value in the coordinate plane and a y value in the coordinate plane, and the radius, which again we'll talk about later, but now you can just think of it as a slope made by these two values here, or you could even think about it as the side drawn to connect these two values here. But now we've equated it, we've done some hairy algebra with it, and now we simply come up with that the cosine squared of theta plus the sine squared of that same angle theta will always equal 1.